So my name's Alex, and I'm going to be presenting some work across a consortium that we have going in the UK and have had going for a little while now. So in this presentation, the objectives that I want to go over are, firstly, I'm going to start off by giving some of the big picture, the kind of application of where we're coming from in this sort of space. I think that's really important to do, to see for how it is we're coming to look at biodegradable transient electronics and have a roadmap to get us to this point. And actually, we'll see a lot of overlaps with the previous presentation. We're very interested in healthcare applications, and we're coming towards the same thing, but from a very different starting point. And it'd be interesting to look at the pros and cons of those different approaches. And then I'll move on to looking at the technical work here, where we were looking at using Pullulan as a substrate, which is a commonly used kind of drug biocapsule material, and then looking at zinc for doing conductive interconnects. I always like to put the acknowledgements at the start of the presentation, because it's really important to acknowledge that this is lots of teamwork. The bulk of the technical work in this presentation was actually done as a partner in the consortium known as the Centre for Process Innovation in the UK. And they're kind of designed to sit between universities. So I'm in a university and I do small scale prototyping. And they sit between universities and then industry. And so they've got kind of pilots, roll-to-roll lines, and scale-up compatibility is a big part of our work. And you'll see that driving some of the decisions that we make later on. So kind of in terms of my lab at the University of Manchester, we're interested principally in wearable devices. Okay, so the same sort of things as we heard about in the last presentation. But these are kind of commercial type ones that we've got on the slide there. And of course, there's a wide range of ways that we can make them better, right? There's technical opportunities in terms of introducing flexible, stretchable electronics. There's some less technical ones about kind of co-design with users, addressing some of the personalized sensing, the health inequalities, digital exclusion that these sort of things start to introduce. Because what we do see is very much, at the moment, these devices at the top all look very similar. Physically, they're very similar looking devices, all measuring very similar looking things. And we've got lots of opportunities for introducing flexible, stretchable electronics or going beyond that. The direction in that, I think this audience is very well known. It's to start to look at the sort of e-skin, epidermal electronics, the sort of things we saw in the last presentation. The example at the end there is from John Rogers, very well known in this sort of space, with the kind of skin conformal, Sexable electronics. And of course, it's not just these are smaller and more socially discrete, but they can, because you get very good contacts to the skin, you increase the surface area of the connection, and that can really drive up the signal quality that you get. That adhesion work that we saw in the last presentation is really fantastic for this sort of stuff. So if we look at the kind of cross-section of making a wearable type of device like that, now this is how we go from you as a person, whatever parameter it is you want to sense. In my lab, we would be 99% non-invasive. Most of the stuff we look at is on the surface of the skin. And we're going to go through some electronic circuit blocks up to the cloud, doing some data processing there, or possibly online. And then, of course, coming back the other way. That stimulation actuation route is a really important part of next generation wearables. And so my lab today has activity across that complete spectrum, in all of those different boxes that we've got going on there. Sort of things of interest, so this audience is very much about the flexible electronics, and of course we're starting to move into the sustainable electronic aspects. But we do lots of work, for example, just with off-the-shelf wearables. So we're doing a number of projects, for example, with long COVID at the moment, supporting clinicians use off-the-shelf devices to get data and insight and look at interventions ultimately in long COVID. And of course, we're, like many people, interested in full closed-loop devices. So looking at light generation, they're looking at it for doing non-invasive neuromodulation type stuff, and really kind of a complete spectrum of sense actuate devices. So if we take a look at our current status, we've got kind of complete printed electronic sensor nodes. I'll show a zoom in a second. We're not looking at Sexable, we're only looking at flexible. And at the moment, we measure parameters like activity, like in your Fitbit, and heart rate, ECG type information. We're actively looking at printed batteries to go along with this at the same time. And equally, we're also looking at roll-to-roll manufacture of these. So I'm not going to go into our scale-up in this presentation, but we're very interested in not making one of these in my university lab, but making that spectrum. I can make one in my university lab, knowing that we can make a kilometre, however long of them, in our pilot line at CPI. In terms of that sort of sensor board, this is probably a fairly familiar sort of material stack for people here. So for the roll-to-roll type processes, we're looking at a PET substrate with silver on it and then a UV cured dielectric and conductive paste mainly for the component mounting. So that's our kind of starting point. That's where we're at the moment. And so, of course, the question is, well, where to go next, right? And we've got a few different avenues. One, very much looking at the, going beyond those easy dry modalities like ECG accelerometry, looking at the more biosensor, wearable electrochemistry type stuff. And then also looking at the sustainability, which is very important. So the example here is carbon-based tracks on a paper substrate. And I think we're going to see a few examples of other people doing similar approaches at this conference. Like everybody, sustainability is an increasing part of our agenda. At the moment, we're using silver on plastic. It's not, up there in terms of the sustainability. And we're really at the point of just starting this journey. And so that's what we're doing in this paper that's in the proceedings, just looking at a few different options for what can we do. From the slide here, we've got carbon on paper. In this particular work, we were looking at doing zinc on Pullulan. And I say this is just us exploring the design space, seeing what might work, what might not work. Just to say briefly, again, if we look at one of those kind of epidermal tag type things, this is my cross section of that. And I think we've got 10 different materials areas to be working on here. In terms of biodegradability at the moment, I'm principally looking at the substrate, number 3 there, and the electronic interconnect for conductive tracks, number 6. And of course, it's really tough in many ways because until you tick all of the boxes in terms of your biodegradability, you've still got potentially some bits like your microchips. Say, we're doing a hybrid integration approach, so we've got bog standard microchips that even if a substrate is biodegradable, they're still going to be left behind. It's going to be a long road to tackle transient electronics in all of these different areas. But what we wanted to look at here, we looked at sputtered zinc on Pullulan. So there's 3 different parts to this. So firstly, the manufacturing method was sputtering, a very common technique. We were looking at that because it's roll-to-roll compatible. Okay, we're not doing roll-to-roll in this particular work, but we know we can add this onto our line if we wanted to. We looked at zinc as a material because it's reasonably conductive and it's got good biocompatibility. So you've got a recommended amount of zinc each day that you're meant to have as part of your diet. So these aren't ingestibles, but in principle, it's good for you to have some zinc. And then Pullulan, we chose because it's widely used as a biodegradable substrate. It's used for classically for kind of drug capsules, so it kind of dissolves when it gets wet. So what we did was sputter on some zinc, comparing the performance that we get with 3 different masks for doing that. And we used a dumbbell shape, as we have here, which is a shape we've used previously, both for doing ECG electrodes, so for measuring heart rate, and also as a UHF RFID antenna structure. And so we can see that we've got some fabricated structures there. We see quite an impact of the mask that we choose to use. So using the Vitmara mask, that's the only one where we can get a 2 millimeter resolution. So there's a gap between these tracks here, which is 2 millimeters. If we do the others, they will bleed together. So we are looking at pretty large structures here using this manufacturing technique. But we could get to pretty good electronic performances coming out. We could tolerate, very decent size currents, 100 milliamps or so, 1.3 ohm per square of conductivity. And then if we look at the breakdown of that, so this is the zinc on Pullulan being put into distilled water. And we can see over the course of a minute or so, I got through that, it is going to break down. I don't have anything else to say about this place. Maybe I should put it on 2 times. So you can see it going into the liquid there, and particularly when you see it start to break down, basically immediately, and in a second or 2, it's going to be given some mechanical prodding, and you can just see it start to dissolve away. And fundamentally, that's what we were looking for in this work, to look at a bit of the degradation and a bit of the electronic properties. We're looking at quite large structures, but we can make them. The RF performance isn't in the paper. It was extremely poor, is I think the summary. And of course, we did the classic. It degrades too quickly. It's very easy to make transient electronics that are very transient. As soon as this gets wet, it starts to degrade. And so that's going to really limit where you can practically use it. There are some chemical modifications you can do to the Pullulan substrate to try and change that. And that would be something to look at into the future. But so this is one of a few different approaches that we're looking at towards taking our silver on plastic electronics and making them more biodegradable. Thank you.